Hey guys, it's Sebastian from Stellar Tutoring, and today we're going to be going over rate of change, which is one of the first real calculus concepts we see come up in, calculus class. So what does rate of change mean? What word do you think of when we talk about rate of change? Now, if you had guessed slope or gradient or incline, whatever you call it, you'd be right. So why don't we go back to some of our algebra or pre-algebra work, depending on how you were taught it, and find the average rate of change or the slope of this linear equation. So usually what you do is you choose one point, as I have here is 0, 0, right? And then you choose another point. So let's say here, 2, 4. These are our 2 points, and then we use our handy equation, which is y2 minus y1 over x2 minus x1, which basically means, or which exactly means, the change in y. So we write change in math and science with this symbol called delta, a triangle. So our change in y over our change in x. These are just two ways of writing the same thing. You don't have to worry about this one because you're usually only taught the one on the left. So when we plug it in, we have 4 as our y2, 0 as our y1. And as our x2, we have 2, and our x1, we have 0. 4 over 2, the slope is 2. Boom. And we can look at that here. The rise is 4, or the rise is 2, and the run is 1. Simple. And this is true throughout the entire graph because it's linear, it's a line. If you choose this point and this point, it's no different than if you chose this point and this point, right? So that's what's not special, but what helps us identify these linear slopes. But in calculus, we want to expand on this idea. We want to go not only on linear equations, but we want to work on curves, on quadratics, on, sine and cosine, and all these things that aren't a straight line, or polynomials, for example. So let's look at this graph here on the right. We see we have a curve, but why don't we try applying the same idea? And let's change the color so we can keep track. Why not try finding the slope between 2 points? So let's choose 0, 0. And then, oops, we can try this other point over here, 1, 3, right? So let's just act as if we're doing our average rate of change or slope formula. So our 2 points are 0, 0 once more, and then 1, 3. So let's calculate. 3 minus 0 over 1 minus 0 equals 3. So then what that represents is the average rate of change or the slope between those 2 points, or as if we were just to draw a line between them. Now that's our rough average rate of change. As you can tell, these aren't the same line. This is a straight line which kind of undershoots, and this is a curve. So you can say roughly the average, rate of change is around 3. But could you say that's the exact rate of change? No. And what's even more interesting is that unlike in these linear graphs where it's like y equals mx plus b, where the slope m is the same throughout, the slope changes here. So why not, instead of 0 and 3 or 0 and 1 for x values, why don't we try 1 and 2? So this is going to work out to 1, 3, and then 2, 2. Let's try that. 2 minus 3, this is some algebra. 2 minus 1, we get negative 1 over 1, which simplifies to negative 1. And if we were to visually represent this, we would see it's a line connecting these two. Now, as we see, it's still not accurate. This undershoots and then it overshoots. It's not a perfect representation. So how could we approach that perfect representation? Well, why don't we try making the interval smaller? We can get closer and closer to just, having a small little distance. And pay attention to my cursor, like right here or right here. That would get us a more accurate result, wouldn't it? Because we have a smaller interval and we would have less of this, these huge gaps like we see right here, right? So for example, why not, instead of, 1 and 2, why don't we try, and let's change the colors one more time to a nice blue. Why don't we try instead the difference between 0.5 and then roughly 0.6. So 0.5 is going to be our first x, and 0.6 is going to be our second x. Now, what's our y's? Normally, you could look at the graph, for this one or for that one, but we see here you can do it certainly, but it gets kind of hard, and it's not going to be the most accurate thing. So what you're usually given, especially when it's such small changes, is you're given straight up the function. So usually you see f of x, but it doesn't matter what letter you choose. It's just like names, right? So we can call this function g of x. And now I know what this is because I plotted it myself in Desmos. So this function should be roughly x to the fourth minus 3x cubed plus 5x. And we call this a polynomial, right? A fourth degree because, boom, we see the highest power or exponent is 4. So when you're given these small changes, 0.5 to 0.6, where our change in x is roughly, or it's not roughly, it is 0.1, right? Because that's what x2 minus x1 is equal to. And you can test that for yourself, 0.6 minus 0.5 is small, it's 0.1. So to find this, how could we find this y here and this y here? Think about that. Now, if you had guessed, plug it into the formula and see what you get, that is the exact right answer. So, and I had worked this out already, but you can do it yourself on a calculator or by hand if you want to really do it. So if we plug in 0.5, if we replace all the x's with 0.5, we're going to get roughly 2.2. And if we replace all the x's with 0.6, our output is going to be 2.5, roughly. These are rounded. And just as an example, this would look something like this. To the fourth power minus 0.5, minus 3 times 0.5 to the third power, and we're getting a bit cramped, but plus 5 times 0.5. And you put that on the calculator, do it by hand. And then we do the same for 0.6, but I had already worked it out for the sake of time. 2.5. So we have 2 points. The point between here and here, we draw our little line, and I already drew a line. Actually, let's clean that up a little bit. Between here and here. Let's do our good old slope formula. Our change in y is going to be y2 minus y1 over x2 minus x1. And we'll do this down here. It's going to be 0.3 over 0.1, which ends up equaling 3. So again, now it happens to be the same as this 3, but that's just a coincidence. But we see it's approaching. I'm going to have to zoom in a little bit for this one. We see that if we were to connect these 2 points, that line matches up way more than this green line right here. See how it undershot, or how this one undershot and then overshot? But this one is much closer. Is it perfect? No. But we see that as we make the interval smaller, as we make this delta x here, the change in x smaller, what if we had, 0.6 minus 0.59? So our delta x would be, can you guess? 0.01. The smaller we make that delta x, the more accurate the slope at that point, or the average rate of change at that in that interval, in that between 2 x's becomes. So you might be thinking, all right, how accurate can we get with this? And we have just enough space right here. So we see that the smaller we make our delta x, if we go from 1 to 0.1 to 0.01, we get more accurate. It becomes more accurate. What if we made that delta x 0? Now, can we do that? Not kind of. As we see in our equation, delta y over delta x, it's a fraction. And can we ever have 0 in the denominator? No. Oops, I changed to yellow, but we're staying with that. So our delta x can't be 0, but it can approach 0. And this is something we're going to build on later using limits. And the color change, but we're just going to keep it like that, right? What if our delta x approached 0? Not at 0, but approached it. then we'd totally be allowed to have delta y over delta x, where x is a really small number. And that's how we get to the limits, right here. And that's how we find the instantaneous rate of change. So rather than the rate of change between these 2 points, we get the change at an exact point. We can think of our tangent line like this, right? That instantaneous rate. You could tell me, or I could tell you, the teacher could tell you, or the instantaneous rate of change could tell us the slope at this exact point. But we'll get into that later. But as a summary, when you're finding average rate of change, you do the slope formula on the 2 points. Your output, your y2s and your y1s, over the input, right? And the smaller you make that the smaller you make that range of inputs, the difference between 0 and 2 is 2, but between 0 and 0.5 is smaller, right? The smaller you make that difference in input, the more accurate your slope becomes to that specific segment. And if you eventually reach 0 or very, very close to 0, you get the instantaneous rate at a single point, roughly speaking. So that's all for today. I hope you can understand. Feel free to ask any questions, and good luck. La 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 la. Yes, it's recording.